Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about heat pipes and vapor chamber, a refresher so to say. So let's dive deep into it. So what exactly is the problem? Well, problem is as things utilize power, it does not matter whether it's a computer, a gizmo, solar panel or a IGBT of a motor, they get heated. Like that's the law of physics, because again most things are not superconductor, so no matter how efficient they are, they're gonna heat up. And if left unchecked, let that be very clear, if it's like if you did not design accordingly for it, it will cook itself. That's the biggest problem of it, because you're like, hey, it's just a battery device. Yeah, if it is unchecked heating element, it will destroy itself. So fundamentally, we have to figure out a way to deal with it. That is the most critical aspect of it. And be mindful, we have to deal with it in everything. It's not just like a computer, laptop, a smartphone, electric vehicle, industry, it's everything. Satellites included. So fundamentally, it is a very important thing. Now, why this is such a hard thing? Well, you would think, okay, what if I just slam a heat sink of metal into it? Yeah, here's the deal. You will find it odd, but metals are very poor conductor of heat. Like they're bad. Like they're so not efficient. Like we are like, yeah, this is not gonna do. Like this is bad. How bad? Well, the best metal we have for thermal conduction is silver, pure silver. That puppy only goes to 4,290 29 watt per meter Kelvin. That's not good enough. Like for modern IGBTs, CPUs and all that, yeah, that's like, bro, no. Basically, if we had not created a better technology than metal, yeah, we would not have technology, flat out. That's how slow this is. So yeah, and if you look into NASA's basically Parker Solar Probe, and they're like, okay, why they were using titanium as a heat break? It's like, yeah, titanium, when it was going to the sun, it will heat up. But titanium can handle the heat. Cool, awesome. But here's the, what about the electronics? The heat will take time travel, and the elliptical orbit was designed in such a way that it heats up. By the time it starts to conduct, it's like, yeah, I'm going in the cooler side. So it's like, chill, bro, chill. So it's like, heat up, chill, heat up, chill. Many things are like that, including your 3D printer. It has a freaking stainless steel heat break. A metal as a heat break is like, yeah, one side is hot, another side is cold. It can be done, because again, this may sound, again, even with silver, it sounds like, whoa. It's not that whoa. Like, not even close. Like we could not build modern electronics if this was our limiting factor. This is not good enough. Like, no. So that's the fundamental problem. So how do we bypass that? Well, we trick what we call phase change. Phase change is not limited to your air conditioning. It's used everywhere else also. So if you have a working fluid, you have to understand, even if it's not doing a phase change and you have a working fluid that is being circulated, it will be faster than any solid conductor. Meaning, if you have two sources, basically a hot and a cold end, and you are circulating liquid, like your car engine circulating liquid through a water pump, that will be far more conductive than any metal known to man. So fundamentally, advocation is one of the best way of dumping energy. Basically, take something hot, yeet it. That's all you did. Heat, yeet. So that is the easiest way of dumping energy from one place to another. So it works in the same way. That's how your air conditioner works. It cools air and then just dumps that air. That's why it has a fan. So that is the most efficient way of moving heat from one place to another. And then we come to the phase change aspect of it. First, you want to have a fluid, because again, fluid will bitch slap any solid any day. And then phase change gives you the extra edge, including temperature locking. So fundamentally, phase change of water takes a lot of energy. My apologies. Basically, phase change of water takes bonkersly large amount of energy. How much energy? Well, it takes energy when it is going from liquid to gas, gas to liquid. What does that mean? That simply means if you have ever experimented with a water pan with a thermometer on it, you will be like, okay, you start the system. Let's say ambient temperature was 30 degrees Celsius. It started with 30, cool, awesome. You are waiting. The heat is dumping into from your gas burner or electric stove. It's going YOLO on it, and then it goes to 100, and then it starts to chill. It's just like, yeah, chill. It's just like, bro, I'm not going to go above 100. No matter what you do, it's not going to go above 100. Why? All the extra energy you are dumping into it is going into that flat line. That flat line is what we call latent heat of vaporization. Meaning, you literally created a scenario where even though you are dumping heat into it, you can't overheat beyond a certain point as long as you have water. So somebody figured out that's a very awesome thing. That's the phase change magic. Temperature does not change. Basically, 100-degree vapor, 100-degree liquid. So how much energy we are talking about? If you are moving heat, that's what we are talking about. Conducting. Metal is not good conductor. So how would you conduct? Like how would you this puppy go? Well, this puppy can dump around 2.26 kilojoule of energy per gram. per gram of water has that kind of energy capacity when it's going from evaporation and condensation. So bonkers amount of heat can be taken from one place and dumped into another place. Now here's the deal. If you're like, okay, if we use with water, cool, awesome. Let's say it can keep the things cool at 100 degrees Celsius. That's not good enough. Your mobile phone will fry itself if it has to go to 100% and 100 degrees Celsius, only then it will start to cool down. That's not okay. Thankfully, water temperature, boiling temperature is not locked variable. It's free variable, meaning throttle the temperature, pressure, so to say. And then you can change the temperature required. Basically, if you are running a coal power plant, you will pressurize it. Benefit, it will require 200 degrees Celsius to boil, or even higher than that. And when you are in this scenario and you're like, hey, I want my SoC system on a chip to be cool enough, you're like, okay, let's cool, drop the boiling point to 30 degrees Celsius. Like, how would you do that? Well, you create a partial vacuum. How low? Well, generally we are looking at 0.8 psi. So that is generally the lower temperature that we have to aim for. Now be mindful, that's not necessary, and I don't think modern sims are designed for 30 degrees Celsius. That's too low. Like ambient temperature, most places are, especially outdoor, is above that. So you may design for 35 or 45 degrees Celsius. Basically, you will keep it below the operating temperature of your SoC. So SoC has some wiggle room, so to say. So again, it will conduct, it will start to conduct, and it will make sure no matter what happens, it will not exceed 30 degrees Celsius as long as the whole thing cannot dump heat anymore and the water inside has been cooked off. So that's the whole awesomeness part of it. And how much energy we are talking about, like how much oomph it can carry from one place to another. Generally, you will say this sort of example where you like put a copper pipe and same diameter of heat pipe, and you're like, whoa, the energy conduction is bonkersly fast. To mathematically quantify it, copper is 385 watt per meter Kelvin, which is not that great. And again, but not that lower from silver compared to the lowest grade. Like if it's an industrial product, it cannot go below this 5000 watt per meter Kelvin. Yeah. And by the way, that's the lowest. A vapor chamber can exceed that, like by a few zeros extra. That's how fast this is. Meaning it's horrifying how fast it is. Meaning there are some companies who made scoops that had basically a type of heat pipe, and you could just scoop the ice creams and it will literally float it. It was very easy to do. It just hurted your hand because all the chill, basically your hand was like, you were giving your hand a frostbite, so to say. So people were like, yeah, that's not desirable. So, but again, conduction, again, metal conduction is not fast enough. But this puppy is like, I am fast. And it equalizes that. That's another aspect of it. It will make sure every square millimeter of the surface has the same temperature. So if you have done your experiment in school where you are boiling water in ambient temperature by utilizing vacuum on it, same thing. And again, you have actual circulation. And again, circulation does not require pump because it's the heat energy that is doing the work. That's the magic of phase change. That's how you can go from 385 watt per meter Kelvin to 5000. So this also has another benefit. The temperature does not rise too much, because if you are directly using normal copper heat pipes, copper conductors like power electronics and all that, it has to heat up a lot so heat can travel far enough. So the core temperature could go bonkersly high. So that's the phase change aspect of it. That's how what we utilize. Basically, a liquid moving around will carry more heat compared to direct conduction, and going phase change gives you far more energy carrying capacity. So fundamentally speaking, is you are talking orders of magnitude better, not just a little bit better or a little bit less, no, orders of magnitude better. So how these magical devices are created? Well, fundamentally, you are creating a chamber. You have to be mindful of that. So it has to be strong enough to handle it. You can make it out of anything. If there are certain requirements, people have made it out of stainless steel. Generally, they are made out of thick copper. Copper is a good conductor. And you can make it out of silver if you're rich enough or you are dealing with aerospace. But again, it has to be thick enough where it does not crack or let the vacuum escape, so to say, or gases inside, so to say. So you have to make sure A, it's conductor, B, it is strong enough to handle that. So it should be able to handle 15 psi of pressure from outside in. So that's the first requirement, a chamber, a conductor that can handle all this thing. Another aspect is working fluid. That's the main essence. Now working fluid, 99% of the time, it would be just pure water, but not all the time. Specifically, if you are dealing with thermosiphons, specifically in Alaska or Canada, those sort of scenario where you are dealing with permafrost, water will just freeze. So we generally use ammonia in those sort of scenario. And they are also used in satellites and all that, because again, it will not freeze at very low temperature. So that's the good part. Methanol is also a good substitute, but here's it. These things Water, most things go YOLO, GG. Ammonia, very low temperature, GG, and it does have a bit higher capacity. But if like, what if you want to deal with nuclear reactor, like NASA's kilowatt power reactor, which is a 10 kilowatt reactor, it's like, you need hundreds of degrees Celsius. Yeah, use sodium. It has sodium heat pipes. So you basically, based on your requirement, 5 to 10 people on this planet know how to build this thing, and industrial people are like, yeah bro, I got this ammonia one, and 99% remaining one is just like, we are using water. But be mindful, pure water, as pure as possible. And then so you have a chamber and you have a working fluid. Then the last thing that you have to design is the wicking material. Now wicking material is the one that circulates the fluid. Basically you have a heat load, you go YOLO here. So what happens? The water boils away. Now water boils, it goes there. Again, water is a gas at this point in time, a vapor. So it equalizes, it tries to find place where it can dump, because again, it has high energy, it is moving around, it is equalizing the temperature. Then it goes to the cold end where it's actually cool enough for it to condense. Okay, cool. How the heck it comes back? Well, it comes back through the wicking action, basically capillary force, so to say. And that's the critical aspect. How the heck you design a wick that comes back? So far, you generally have 4 options, 3 in mass production. So one option is sintered powder. Most high-end ones will have that. Then you have grooved one, bit cheaper, generally suitable for low power applications. And then you have screen one, generally used for mobile phone. So these are the 3 options. And these 3 options have their 3 power capacity. For example, if you are dealing with less than 20 watt per centimeter square, which again, mobile SoC, you will use a screen one. And if you're like, okay, but it's a bit more heavy, like let's say Raspberry Pi or a router or things of that nature, you may be looking into 30 watts per centimeter square. That point in time, grooved channels would be utilized. Again, it's cheaper to manufacture. But if you're like, no, I am talking about AI card from NVIDIA drinking kilowatt of power. Yeah, you need 500 watt per centimeter square. Now you may be like, okay, 500 watt, like aren't my graphics card can consume 800? Yeah, it can consume 800, but it's not emitting 800 watts of energy from 1 centimeter square. That's not happening. It has multiple centimeter square. So 500 watt is more than enough. For sintered powder. Now there is one other option, that is fine stranded wire, where it's just like how you have solder wick. Put that same thing. You can build it in home also, as long as you can pull vacuum and solder it reliably. You can build it because again, sintered powder is very expensive, grooved thing, God knows, and screen not capacity enough. Then fiber fine is there, but again, I have rarely seen that utilized in most places. So if you know where those are used, do tell me. These 3 I know, but that I do not know. So these are the options of the construction of a variety, meaning if you're trying something cheap and easy for low power application, go with screen. If you're dealing with something bit mild power, go with groove. And if you're like, okay, I do not want to deal with this, get sintered powder. But again, be ready to pay for it. It's gonna be expensive. Sintered has like the best surface area, so capillary action is maximum at that point in time. Grooves, they do have work, but they do have the penalty that they cannot fight against gravity that well. So if it's a known thing, is established in a known scenario, it's good. But if it's you're not planning for that, it's like, okay, it has to be like a smartphone or smartwatch. Yeah, not desirable. So construction has to account for all of these things. That's why most laptops do not have vapor chambers. It's very expensive, like very time consuming to design for it. And if like, what if I take the heat pipe and squish it, you would be shocked how much energy it loses. Basically the conduction goes down drastically. Even I was shocked, like how badly it loses conduction. So let's come to the core aspect of it, the efficiency. And whenever you're talking about any scientific thing, sooner or later it will always come down to coupling efficiency. I'm making a laser, does not matter how much energy conversion efficiency you're getting. I'm making a bulb, it does not matter how much conversion efficiency. I'm making LED, how much conversion efficiency. So coupling efficiency is the key, basically how much actual work you are getting done. Now, every thermal solution has this one thing. Hot to ambient, the end, there is nothing more than that. So the key is to reduce resistance. Now one core aspect you have to understand, like if you have seen my hard drive caddy project, I worked very hard to make sure the hard drives were naked. Why? If you're like, okay, I have a hard drive, I'm gonna put it in a caddy, metal caddy, and I'm gonna put it in a system and I'm gonna blow air through it. Yeah, hard drive is covered by insulator. It's like, that's why I specified metal is an insulator. If you want to keep something cool, you want it, the conducting medium directly touching it. Or something phase change like or liquid cooling. But if you just have air, that's a bad idea. You generally would be better off if you have it naked. So you have to pay attention to this. This is what we call basically interface resistance. Every time your heat source, let's just say silicon in computer has a heat source, right? That's the hot part. that has to go through basically what we call integrated heat spreader. It's done for safety. It's not required. It's just done for safety, for stupid proofing it, so to say. But again, every time you are going from silicon to copper, heat bounces backwards. Anytime you have interface, heat does not just like, oh, heat is here, heat goes here. No, no, no. It will bounce back. So you have a resistor element. That means this has to get extra hot in order to dump all the energy. So your temperature already risen up. And then that heat spreader goes through a thermal paste. Again, that same problem. And then another cold plate of the basically heat sink, another loss happens. So and that's why GPUs generally do not have that. They're like, nah, bro, we can't cool it if we directly have a die cover there. That's why their dies are naked. You can see it. Same goes for laptop. Basically, it's not about the how much kilowatt it has or TDP it has. It's just how efficient it is. Meaning you can cool a very power hungry desktop CPU in a laptop cooler as long as it's efficiently coupled. So coupling efficiency is there. If it's a naked die, you can cool it much easily. If it's able to expand its heat efficiently, it will work. So interface itself, basically the best solution is reduce the amount of interface you have, meaning how many times heat has to jump from one to another, reduce that, the best outcome you will have. And vapor chamber is basically bigger brother of heat pipe, simply because heat pipes geometry wise is one dimensional. It just takes the heat in one axis. When you are comparing it to vapor chamber is two axis. So that's why vapor chamber is bonkersly high thermal conductivity, bonkersly high. Like that 5000 is like, bruh, like that's a horrendously bad vapor chamber if that's how it goes. So you are looking at this, something that can easily handle 100, 200 or even 300 watts of TDPS. Like how? Well, first it has very high power fan blowing through it. Second, vapor chamber. Now vapor chamber's main asset is that it can take heat and equilibrate along a much larger surface area. What does that mean? That simply, let's say you have a PlayStation 5 heat sink. This is not exactly PlayStation, but you get the point. You have a SoC. SoC is dumping heat, but again, it's metal heat sink. Somebody chipped out on the wrong place. So it has to heat up. Again, conducting is not fast enough. It's taking its sweet time. Heat is going there. And it's heating up because again, it can't push heat enough. It's like there is no working fluid there. So nothing is taking it. Nothing is eating it. So it heats up, heats up. By the time it goes here, it's like it's already fried. You have so much mass, but it's not being utilized. That's why you put heat pipe. We put heat pipe from here to here, so it can actually use the goddamn mass that you are putting into it. That's why you see even a smaller cooler is like, oh, heat pipe is going from the bottom on the top. Why? It's more quicker to go from heat pipe to the heat fins rather than just going through the heat fins. So this is the problem that we deal with. Vapor chamber, on the other hand, the moment you put it on top of SoC, it equilibrates the whole bottom surface of the whole stack. Now every single area of the stack is at the same temperature. Now the conduction efficiency is very high, meaning this heatsink allows your CPU to run at much lower temperature, even though the TDP, as in total power dissipation, is exactly the same. So that's what we want, and that's how server cooler works. Because again, they take the die, and if you look into IBMs, they do not have what we call basically integrated heat spreader. That's more of like x86 things. Most other designs, even basically from Microsoft, their own silicon, most of them are naked nowadays. IBM's industrial grade payment processors, almost all of them are naked. NVIDIA's high-end systems, most of them are naked. So they generally dump the heat into this puppy. This puppy spreads it out, like it goes wabam, and it can do with hundreds of watts or even kilowatts. It just spreads it out everywhere, and then you have to dump it into a fin. Now here's the deal. If you look into normal CPU cooler, it's a very hard process to dump heat from your silicon to final heat fin that has the air contact. Why? Because heat pipe, even though let's say your heat pipe is hot, there is an interface. That interface is weak link. Even if it's a soldered thing, it's a weak interface. So how do we solve that? Well, we started to shave copper. So this is how you take copper and you just shave it. And you make basically fins that are physically one element. Basically, grain boundary is exactly intact there. It's not soldering, it's not welding, it's nothing. It's literally same grain boundary. So heat can jump from here to there without any issue. From heat point of view, this is one item. It's not like, okay, I'm going from to this to, no. This is just one item. Go home. So that reduces the amount of basically jumps it has to do. So a server can easily have a silicon die, directly jumps into vapor chamber. Vapor chamber directly dumps into skewed heat sinks, basically shaved heat sinks, and done. Done. Now you have air directly blowing through it, meaning you can have much higher thermal capacity simply because you have reduced the interface count. So skewing heat sinks are the top of the food chain right now. So you have a vapor chamber and skewed heat sink on the other side of it. The end, go home. That's the best as of now topology we have. The only thing that we can beat that is like you have to put a refrigeration circuit. Other than that, nothing else. So this is the most efficient design. And again, you have to think through this. It's like you can look into old CPU coolers. They used to have a like cold plate, then they had heat pipes, and then they're like, okay, heat sinks. Now it's like, okay, heat pipe has to actually touch the damn thing. So now they're like, okay, let's touch the surface. And again, the ultimate option is what servers have been using, but again, they are expensive. So, but that's the ultimate. Basically, you spread the heat in XY. You do not, oh, this place has the die. No. The vapor chamber is like, I am the die. It just spreads out everything instantaneously. Not instantaneously, but like fast enough where it does not matter. So what can we expect in the future? Well, reality is more and more things are moving towards vapor chamber, because again, I have specified we could not have built our modern electronics without basically vapor chamber and heat pipes. So heat pipes got us so far, but we want to push more. So we are like, yeah, we have to go from single vector axis to dual axis, like you're going surface area. So that's why more and more designs are utilizing vapor chamber. Now, vapor chamber in mobile phone, they are going through simple dimension. It's like they want to make it as cheap as possible and as slim as possible. I've seen some claims, which again, I have very hard time digesting it. They are claiming 0.2 millimeter vapor chamber. I'm like, that's paper. So somehow they have figured out how to have all the layers, and that's how allows your phone to actually have enough power, because again, it's not dumping the heat, it's just spreading it out. Basically from that point, it's like, so instead of that point going to 50-60 degrees Celsius, it's just like 30 degrees Celsius, because it spreads out so much. And the cheaper option is having a graphite sheet. Again, graphite sheet in XY does have the same kind of efficiency. Not as good as vapor chamber, but if you do not want to have anything else, that's the one option. Because again, right now, nobody has finally figured out a way where you can wrap this thing. That would be the next evolution, where you can have like SOC, vapor chamber, and vapor chamber wraps around the battery. Then it will have enough surface area that it can handle even high-end SOC without any issue. And again, SOC will also get more efficient, so meaning thermal throttling will just become impossible to do, simply because unless you are roasting it, or in India, in rooftop, 55 degrees Celsius. So that's the development on the system parts. And thermosiphons are also making a very interesting comeback, because that's already a heat pipe. It's just that instead of a wick, it generally relies on gravity to, because again, it has to be gravity sensitive. It does not have a wick structure, and people have been trying it to make for desktops, but problem is not designed for that. Like all the engineers that are for thermosiphon, most of them work for industrial sectors. They are like, okay, we are working for permafrost to make sure permafrost never thaws out, or building Alaskan pipeline, so make sure the pipelines are always at the right temperature. Those sort of people. But again, people have been trying to make this puppy into a thing. As of now, it does exist. It's just an art piece, so to say, Lamborghini. It's not practical. It's not Toyota. So let that be very clear. It's all about coupling efficiency. You can look into this cooler and you're like, okay, this is 150 watt TDP, and this is the same cooler. It is 180 watt TDP. It's like, how the hell that happened? Well, vapor chamber. Vapor chamber is spreading the heat out in two axes. So it's like a stick versus surface area. So fundamentally, that improves the thermal capacity without any discussion. Like we do not have to discuss. And because the back end of it is thermally skewed copper systems, ta-da! So it takes the energy, spreads it out, dumps it into the fins. There is no interface. The end. So this can easily beat out this without any hassle. So it's the key aspect. Now let the vehicle. This is an old technology. Server people are like, bro, we have been there, done that. Why are you talking about it? It's just that now it's starting to come for AM4 and AM5, and cheap enough. So that's what future is like looking towards, making super cheap, super flexible, basically vapor chambers for your mobile phone, and as much development as possible in thermosiphon, which again might be making a comeback for electric vehicles also. So that's there. And another aspect is making everything as better at coupling as possible, because it's not about like, oh, what is wrong in this. It's just poor. It's like the amount of copper, the amount of silver, the amount of, again, silver sorter and all that you're doing in this, you can do much more with less. That's the aim. That's what we want to do. So more and more things are moving into vapor chamber again. And remember that you are going from one stick to surface area. That's why everybody is like vapor chamber is the future. So this was my presentation on basically vapor chamber and heat pipes. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.